I am going live. What the It's a differential equation, bro. Chat, we're back again. We're back again. I don't fucking know. Dude, Like, what the fuck, dude? It's a differential equation, bro. What do you mean you solve everything using u subs? You don't need a u substitution for this problem, dude. I'm sorry, man. Like, I can understand for infinite series. Hold on, I'm sorry. I thought like cause I think my clip microphone is incredibly sensitive. Um, you don't need u substitution for this, bro. Look at that. I already solved the differential equation. Did that involve u substitution? No. That's like no, man. Sorry, I. Hold on, I'm re-announcing in threads. The fuck? Yo, chat, join up. Join up, chat. Okay, I'm just gonna continue even without viewers. Let's continue. Okay, so I really wish that I have a stable internet connection now. Okay, here we go. So number two, question number two in our daily differential equation. Um, we have. Oh wait, we forgot something. We forgot something in our solution. Okay, so they were asking for y of -1. So what's that going to be? That's actually just going to be simple. That's going to be the negative nat of the natural log of 2 minus 1 all over e. And yeah, that's our answer. That's our final answer. Okay, so medium differential. Medium medium differential. So this was yesterday's medium differential. Number medium differential. Let's just say this is question number 2. Okay, so let me read out the problem for everybody. So Susan is peeling a banana inside a dimly lit neuroscience lab while a synthetic axon fires pulses across a glass chamber. The banana peel displacement is x, and the voltage intensity of the neural signal is y. The lab computer reports that dy over dx is equals to y plus x cosine of y over x all over x, given that y is equals to 0 when x is equals to 1. So I think that means y of 1 is equals to 0. Okay. So I think that's what they're trying to say here. Okay. Okay, this time we're actually going to use some kind of u substitution, and one of my viewers are apparently incredibly obsessed with this. One of my viewers are incredibly obsessed with this, so we might actually use a u substitution. Okay, so I'm gonna rewrite this differential equation as something like this. Okay, so now we can go ahead and rewrite this as dy over dx, and that's equals to y all over x plus a cosine of y over x. Okay, now we have a common variable here. We have a common term here in our differential equation, and that is y all over x. So I want to introduce u of x, which is defined as y of x all over x. So y is therefore equals to x times u. I mean, if we multiply both sides of the equation by x, we're going to get that relationship. Okay. Now I want to differentiate. So dy over dx is equals to u plus x du over dx. And then now let's go ahead and substitute that into our equation. So we defined dy over dx as this expression, right? So we defined that. Okay. So we defined these variables. So let's go ahead and just substitute. So we have u plus x du over dx, and that's going to equals us to u plus the cosine of u. And here, finally, we're going to use the u substitution, right? This is the u substitution that you asked for. Okay? Holy shit, what the fuck is that? The sound, dude. Hold on. Okay, the screech have lowered a little bit. So let's continue. Okay, so look at here, we can go ahead and cancel them. That's not needed. And now finally we have this very nice equation. Very nice, very good. So finally we have this. Now I can go ahead and separate the variables. I want to separate the variables. So we have 1 all over cosine of u, which is just secant, by the way, du, and that's equals to 1 all over x dx. So let's go ahead and rewrite our new equation. So we have secant of u du, and that's going to equals us to 1 all over x dx. And now we can go ahead and integrate both sides of the equation. Um, so the integral of secant of u, the integral of, okay, so I think that's natural, if I'm correct, that's natural log of secant of u plus tangent of u. Why does it take up space so much? It's annoying. Equals the natural log of x plus cheese. So if we were to exponentiate both sides, we're just gonna have this. Pretty simple, right? Okay, so let's go ahead and initial value. So y of 1 is equals to 0. So u of 1 is also equals to 0. I mean, why? I mean, literally why? If we were to input, if we were to input 1 as x right here, this one is going to equal to 0, right? Well, of course, 0 divided by any number except 0 is going to be 0. So yeah. So using that initial condition, so we have secant of 0 plus tangent of 0 is equals to 1. So 1, because we did say c of x, so 1. I mean, this is 0, this is 1. So c must equals to 1, right? So we have this general solution, which is equals to x. Now I want to solve for u. Like, we need to isolate u here. We need to isolate u here. Okay, so let's use the trigonometric identity, which is secant of theta plus tangent of theta, and that's going to equal us to tangent of pi over 4 plus theta over 4. Wait, shit, no. Wrong identity? the denominator is supposed to be 2. So in that case, if that is the case, then we must have this identity too. So we have tangent of pi over 4 plus u over 2 is equals to x. Now this is our new equation, right? Now in order to isolate u, I want to inverse arctan both sides of the equation. So we have pi over 4 plus u over 2. That's going to equal us to arctan of x. And then boom, look at this. So if we were to isolate u, we have u of equals to 2 times the arctan of x minus pi over 2. And we did say that u is equals to y over x. So multiplying both sides of by x, we're finally going to have this very nice general solution, which is x times 2 arctan of x minus pi over 2. And that is our solution to the initial value differential equation. Isn't that very neat? You even use u substitution in quadratic equation. Wow. You're just like me, but it's infinite series, dude. Wow. I guess we do share something in common. I mean, the math community gets weirder and weirder every day. Okay. Where are we? Where are we again? Oh yeah, y to the e. Y to the e. I mean, that's just simple. That's literally just simple substitution. Like, look at this. E times 2 arctan of e. Arctan of e minus pi over 2. Boom. And that's our solution. That's it. That's literally it. It's so easy. Now here is the hard differential. This was yesterday's hard differential, right? So I need to solve this following differential equation. Alright? So chat, here's what we're gonna do. Here's what we're going to do. This is not even done yet. There is an initial boundary, I think. Initial condition or in the initial boundary? I think it's boundary in this case, if I'm not wrong with the terminologies. Wow. The screeches, bro. Anyways, can you differentiate 2x using infinite series? Well, you'll see what I will do here, right? If you want, like, okay, this is our moment. This is the moment where we use power series for the first time in this stream. This is my infinite series skills in action. But first, let us acknowledge the initial conditions that was stated in the original problem yesterday, because I didn't manage to answer it on dailyintegral.com. But probably later I'm going to buy it using credits, because you can actually access the archive of problems in the website. So yeah. So let's acknowledge the following boundary conditions. Y of 1 is equals to 1. Y prime of 1 is equals to 2. However, y of 2 is equals to this. Now you may be wondering, what the fuck is this? And that is exactly what we're going to determine. That y of 2. What is that fucking thing? We're gonna find out. So first, let's solve the differential equation. And we're not going to use the standard power series, because x equals 0 is a regular singular point. So instead, we're going to use the Frobenius method. So assume that y of x can be expressed as a Frobenius power series. Let me show you. Alright, the sum from n is equals to 0 to infinity of a of n times x raised to the power of n plus r. Now there is a r there. You'll see why, because we're going to involve something called a indicial equation. So dy over dx is going to equals to, okay, let's just go ahead and take the derivative of the power series, right? That's going to be simple. N is equals to 0, n plus r, a of n, x to the n plus r minus 1. Simple power rule. Alright, that's just simple power rule. And then d squared y over dx squared. And so we have the infinite sum. And there we have it. So we're going to go ahead and substitute this into our differential equation. Because you may be wondering, what are we going to do with the 2x? Let's wait. You're going to see it. Alright, you're going to see that. Alright, let me cook. Let the chef do its thing. Alright, so this is going to give us the following. N plus r, n plus r minus 1, a of n x to the n plus r, plus 2 times the infinite series a of n x to the n plus r. What happened? Because we multiplied x with our series here, with our term here, with our power here. Because if we were to multiply x raised to the power of n plus r minus 1 and then times x itself, isn't this just 1 raised to the power of 1? And then 1 negative 1 plus 1 is equals to 0. So that's gone. You get it? You guys get it? So that's why we are now sharing a common power here in our series. And that's actually huge. So now, okay, minus 2 times the infinite series a of n x to the n plus r, okay, standard power series, equals 1. Now look at that. All of these terms share a common power, which is n plus r. So what do we do when there is an infinite series whose infinite power series? There's a power series where they share a same power. We combine them into one sum. Alright? We combine them into one sum. So what's going to happen? Chat, this is what's going to happen, alright? This is what's going to happen. This is what's going to happen. Chat, this is what's going to happen. I'm telling y'all, chat, that's what happened. Now let's go ahead and simplify this. Sorry, I burped. Let's go ahead and simplify this. This is actually just a very complicated way to say n plus r squared plus n plus r minus 2. It's actually just a very complicated way to say that. I mean, if you were to verify it using FOIL method and then grouping like terms and stuff, it's going to yield that same result. So let's go ahead and rewrite it. Alright, so finally we have this infinite series which, hold on, let me write the sigma notation much better. I'm very sensitive when it comes to writing sigma notations. I love infinite series, so I must make sure that how I write the sigma notation is perfection. Alright, there is no room for error. Alright, are you guys following? Okay. Now, the smallest power is x raised to the power of r, because x raised to the power of n plus r is equals to x to the n times x to the r, and that is our smallest power. Our coefficient here, alright, now let's talk about the initial equation. So what are we going to do here in this Frobenius method? We're going to set n is equals to 0, and then we're going to set up that equation. Alright? Wait, the differentiation and integration of any differential equation is just a power series of infinite series? Well, you could say that, but we are also assuming that the solution, the general solution, can be expressed as an infinite series. But how do we prove that it could be expressed as an infinite series? That is, there is a theorem for that. It starts with letter T. I don't know if I pronounce this right, but it's called Toriel's theorem, I think. Or maybe I'll make a video about that, alright? To prove that, okay, we're assuming that this general solution can be expressed as an infinite series, but how do we prove it that it can be expressed that way? Because we're just assuming, right? We don't want to risk mathematical circular argument. So I'm probably gonna make a video about that, addressing that concern, because it's valid. So in this yield equation, we need to find the value of r. So how are we going to do that? We're going to set all of the n's here right now that exist equals to 0, and that's what we're going to focus on. Let me show you. R squared plus r minus 2 a sub o, and that's equals to 0. Why? 1 right here. What do you think in our standard power series? Look at this. N equals 0, a of n, x to the n. In our standard power series, we can expand this as a sub o plus x, a sub 1 times x plus a sub 2 x squared, and then so on, right? Look at that. Technically speaking, right? 1 is a coefficient for this second term. Technically speaking. But here, in our initial equation, we are involving a sub o. And where does a sub o come from? The first term of the series. The first term of the power series. So we can't just equate the initial equation to 1 because they do not share the same coefficient in the standard power series. That's just an example. But even using the Frobenius method, using the Frobenius series, it's the same case. So we cannot equate it with 1. So we need to equate it with 0. Since the right-hand side of the equation is just 1, so technically speaking, if we were to expand the right-hand side, it's just going to be 0 plus 1 plus 0 plus 0 and so on. Why? Because the right-hand side must also follow a series, an infinite series. And that is our infinite series for 1. 0 plus 1 plus 0 plus 0 plus 0 plus 0 plus 0 and so on. Are we following, chat? You sound like math scribbles. Yo. Okay. Alright. Okay. A sub o, this is our arbitrary constant. A sub o cannot be equal to 0. So let's move on. We don't care about a sub o anymore. I know that is harsh, but it's just how it is, alright? So now we're going to focus on r squared plus r minus 2, and that's equals to 0. Let's factor out this quadratic equation. So I don't have to use this fuck-ass quadratic formula. No. R plus 2, r minus 1. Pretty simple factorization, pretty simple factor, and there we have it. We already have our 2 solutions. So now we have 2 solutions right here. So either r is equals to 1, and either r is equals to negative 2. Okay, so I want to use both of these r's for my recurrence relation. So first, let's choose r is equals to 1. Let's see what happens, alright? I'm still not sure yet, but let's use r equals 1. So let's go back to our recurrence relation. And now finally, we can go ahead and involve 1 later. But for now, we're still going to start off with 0. So now we have our recurrence relationship, which is this: n plus 1 squared plus n plus 1 minus 2. Oh, ouch. A of n, and that's equals to 0. Alright. Okay. I was just checking my mic, sorry. Okay. So now that I've chosen r is equals to 1, I'm gonna go ahead and say that, how do I say this? Because I'm thinking like, oops. Let me carefully check my stuff over here. Okay. Okay, so now n plus 1 squared plus n plus 1 minus 2 is equals to n times n plus 3. We can verify that using grouping like terms, FOIL method, and yeah, so on. So we need to state this. For n greater or equal to 1, a of n will be equal to 0. So hence, y sub 1 will be equals to x. You know what? I'm kind of doubting myself. I should probably confirm this because I'm making such grand conclusions. So we have n plus 1 n squared plus 2n plus 1, and then plus n plus 1 minus 2. 1 plus 1, 2, cancels out, plus, so that's 3n. So we have n squared plus 3n. Factor out n, so we have n plus 3. Perfect. Now what? Because if we, okay, so now that, okay, now we can go ahead and rewrite this. We have n times n plus 3, and a of n is going to equals to 0. And since only a sub o is not equals to 0 in this first case, then y sub 1 is just going to be equals to x. This is the homogeneous solution. No, that's not complete yet. X, because r is equals to 1. We chose r is equals to 1. So this is our so we need to complete our homogeneous solution before we move on to the particular solution. Okay, so now I'm going to take r is equals to negative 2. Now the next case is using r is equals to negative 2. So similarly, so we can just go ahead and substitute into our recurrence relationship, and that's going to equals us to n minus 3. N times n minus 3. So again, every coefficient here, except the first one, of course, will vanish. So y sub 2 is just going to equals us to x to negative 2. Why? I mean, of course, x to the r. We chose x to the negative 2. So x to the negative 2. I think this is going to be the very confusing part, because what actually matters here is the interaction and what happens to the coefficients, the interaction between coefficients and what happens. Because we can manually check this. I'm not gonna lie. But the equation does not lie here too. And look at that. that condition right there. So finally, we're going to combine our homogeneous solution, x, and that's going to equals us to c sub 1 of x plus c sub 2 of x of negative 2 raised to the power of negative 2. What happened? Where did these constants came from? It's a format of writing the homogeneous solution. Let a sub o equals 0. No, that it's a arbitrary constant. It's an arbitrary constant. You can't make that into 0. No, it cannot be equal to 0. Okay. Now the particular solution, this is going to be a little bit tricky. Alright? So the right hand side of the equation can be expressed as x is equals x raised to the power of 0. And that's going to give us 1, right? So I want to try expressing the particular solution as some kind of constant alpha. Alright? So when we take the derivative, y prime of p equals y prime, right, y prime prime sub p, and both of them is going to equal to 0. So let's substitute. So let's try to substitute. So we're going to use our indicial solutions here and set up a relationship. Something like this. Negative 2a, and that's going to equals to 1. In other words, r sub 2 times a is equals to r sub 1. And here, r sub 2 is negative 2, and r sub 1 is negative 1. Just positive 1. I'm sorry. So if we were to solve for a, we're going to have a is equals to negative 1/2. So that's how we get the particular solution. It's a little bit still vague. It's a little bit still vague. But that's how I visualize it. Like, I want to multiply negative 2 by this particular constant. Why did I say a? I said alpha, dude. Sorry. Shucks. Yeah. Sorry, man. Okay, negative 2 alpha equals 1, and then alpha is gonna equals to negative 1/2. I think it's also a format to do that, but it's been a while since I've used Frobenius method because I usually use power series method when possible, but in this specific scenario I have a singular point at x is equals to 0. So yeah, that's unfortunate. So what is the answer? What is our particular solution? I mean, for instance, y is equals to c sub 1 of x plus c sub 2 of x squared, because now we're building up from the indicial solutions, and then minus this constant 1/2. Let's see if it's gonna work. Now I want to apply the conditions now. Wait, no. This is the particular solution. This is the particular solution already. And I already combined, this is the full general solution. This is the full solution now. I actually combined the homogeneous and the particular now. Okay, so this is the full solution now. I can go ahead and apply the conditions. So we did say that y sub 1, y of 1 is equals to 1. So let's go ahead and solve for that. So we have y sub 1, y of 1, shit, I keep saying sub, it's not even sub. C sub 1 plus C sub 2 minus 1 half, and that's equals to 1. C sub 1 plus C sub 2, and that's going to equals to 3 over 2, and then so the sum of these constants must equals to 3 over 2. Okay. I feel like we're going to start off a system of equations here. Let's first move on to the derivative, okay? So in the derivative, it's just very simple. And then at x is equals to 1, that's just simply going to give us c sub 1 minus 2c sub 2, and that's going to equals to 2. Right? So now we have maybe not simply a system of equations. It's more like, how do I say this? Let's just figure it out. So we have c sub 1 plus c sub 2, and that's equals to negative 1. Wait, what? Dude, damn. I get tricked by that. Alpha. Dude, that's my particular solution. I said 3 over 2. And then c sub 1 minus 2c sub 2, and that's equals to 2. Is this a system of equations? Am I supposed to solve this? Let me check. Okay. What should I solve first? Okay, I want to isolate. Is this a system of equations? I feel like it is. I feel like it is. Is this a system of equations? Okay, I'm gonna trust chat that it's going to be a yes. So let's solve the system of equations. So I want to isolate. Which one do I isolate? Do I use this one or do I use this one? I'm gonna use this. C sub 1 minus 2c sub 2, and that's equals to 2. Negative 2c sub 2 is equals to 2 minus c sub 1. Divide both sides by negative 2. That's my c sub 2. I'm still thinking if this is a system of equations, or is there a faster way? Is there a faster way? Because I feel like there is a faster way. I feel like there is a faster way, like... Hold on, chat. I'm gonna check something. Because I suck at basic math. Chat, what's 1 minus negative 2? I feel like it's 3. So instead, I want to do this. Maybe I don't have to solve in that kind of method. What if I just subtract them? What if I just subtract them, like, pop pop, they're dead, and then this becomes 3c sub 2, and then these, and then minus these, and now we have 3c sub 2, and that's going to equals us 2. What's 3 over 2 minus 2? I have no idea. I suck at basic math, so please somebody help me here. 3 over 2 minus 2, and that's going to give us negative 1/2. Let's go. And then divide both sides of the equation by 3. What's negative 1/2 all over 3? I also have no idea. So so what do we actually have here? Maybe something like wait, I feel like c sub 2 is negative 1 all over 6, right? So c sub 1 what's c sub 1? Chat, earlier we had that formula. Okay, let's test our theory. C sub 1, so let's instead use the 3 over 2 minus... Okay, sorry. Alright. Okay, fixed it, chat. Chat, I fixed it. Y'all don't have to slime me up. Chat, relax. Okay, C sub 1 is going to be 5 all over 3, and I'm going to be confident in those constants. So, yeah. So finally, y of x is equals to 5 all over 3 x minus 1 all over 6x squared minus 1/2. Look at that. We solved it. Let's go. And then now let's solve for y of 2. And apparently this is the fucking whatever this shit is. So let's just first apply it here. So y of 2, that's gonna give us 10 over 3, and then minus 1 all over 24, since 6 times 4 is 24, then minus 1/2. What is this? What does this subtract to? I think it's 6, 7 all over 24. 6, 7, 6, 7, 6, 7, 6, 7, 6, 7, 6, 7. Let me just check. Anyways. Minus 1/2. Oh my gosh. 6, 7, 6, 7, 6. Sorry. And this is going to equals us to this stupid fucking constant. This stupid motherfucking constant that has no bitches, no friends, no fuck... No, sorry. I mean, I guess third root? Third root of, you know, 6-7 over 24. 6-7 6. Man, you gotta be fucking kidding me, bro. So, maybe not. No. Hold on. Okay, let's first take the cube root of this stupid fucking constant. So y of 2 must equals to something like this. Like, the stupid fucking constant is equals to 6, 7, all over 24, all over 1 raised to the power 1/3. And then I believe y of 2 is simply just equals to the stupid fucking constant squared, which is equals to 6, 7 all over 24 raised to the power of 2/3. And that is our answer. And there we have it. Yo, we did it. We solved the final hard differential equation, and I am fucking going insane. Oh yeah, oh okay. Good night, bro. Oh my god. Am I even gonna wait for the FIFA World Cup finals? I'm probably gonna end the stream early. Like, this is probably not my day, bro. You know what? I have solved enough differential equations. Chat. Yo, chat. Thank you all for watching the stream. I think I'm gonna end it here. I'm probably just gonna do the FIFA World Cup final, the watch party. I'm not sure about this, not gonna lie. I feel a little bit tired, so sorry chat. See you all later.